So what I'm going today is I will start with how I ended last week. I would like to review episode 9, the one where we saw the pricing of exotic options. We saw how we can use pricing to make decisions, or alternatively, I want to explain how decisions can be priced. I will review that. This is part of the dynamic asset pricing theory. And after we finish that, after we understand this way of dealing with multiple time steps, I plan to devote the rest of the day to telling you the framework we will need to be able to do this in continuous time, which means infinitely small time increments. So we're going to go from 2 to infinity. Okay, the big change is to go from 1 to 3, 1 to 2 to 3. Once we can do 3, I will start to go from 3 to infinity without stopping at 4. That's the idea today. The next week, after we developed that way of thinking, where we take infinitely many time steps, next week what I will do is I will show you how that can be used to develop the dynamic asset pricing theory in continuous time and the Black-Scholes theory. But that's for next week. So let me go back to where I left it last week, which is how to price exotic options. And it always, everything goes back to the same thing. I start with the European call option. In this case, I'm taking a call option with a strike of 75, which means that at maturity, if my stock is worth $2, the option will be worth $1.25. If the stock is worth $1, the option will be worth 25 cents. And if the stock is worth 50 cents, the option will be worth nothing. We were able to deal with that by decomposing these time steps into individual branches. Each branch has now a way that we deal with it with the version of the 33-cent game. So this branch here would correspond to this branch here, which allows us to price the option at 75 cents by coming up with the replicating portfolio, which is we buy one stock and we borrow 75 cents. That helps us fulfill that particular branch. This other branch here, we do by looking at the stock, coming up with a replicating portfolio, and realizing that the price of the option is 12.5 cents. And all of that is then summarized for the value of the option today, which is obtained by looking at this. And we see the option price is 33 cents with a replicating portfolio, which is we buy 50 cents to buy 83.33% of the stock. And something key to do that was to realize that whether we get an option of 75 cents or cash of 75 cents, it doesn't matter to us. It's exactly the same. Okay. Now, this is within the realm of European pricing. We just have to wait until maturity, and the payoff happens at maturity. And this is why we attach the adjective European to these options. And the consideration was, what if we can exercise early? What are the considerations then? If we are at the stock price of $1.50 tomorrow, shall we exercise then or wait until the day after when we can make more or we can make less? And what was developed last week is that the way to think about this is by looking into our decision making from a purely pricing perspective. We will make decisions taking into account prices only. So if I have the ability to exercise my option when the stock is at $1.50, what I'm going to do is I'm going to consider the two possibilities that I have, which is to exercise or not to exercise. If we don't exercise, it's European branch, and if we exercise, well, we know what we get, which is 75 cents, so we need to decide. In this case, the decision is kind of irrelevant because the option value, if I don't exercise, is 75 cents because it's a European option. And if I exercise, the stock is $1.50, the strike is 75 cents. So I also get 75 cents. So in this case, I'm indifferent. And the way we think about this in general is always the same. In this particular case, it gives us a trivial situation where we are indifferent. But in general, the way of acting is always going to be the same. First, we consider the possibility that we exercise, which is always the trivial one. We get the value of exercise. In this case, it's 75 cents. The payoff is going to be the value of the stock, $1.50, minus the strike price, 75 cents. So it's 75 cents. If we exercise, we get 75 cents. But if we don't exercise, then it's a European branch, and the value is also 75 cents. If the price was higher, for the case of the European, we would not exercise. If it's lower, then we would exercise. Happens to be the same. This European branch gives us the same price as if we exercise. So this leads to a situation of indifference. Indifference happens very often. In fact, there is a theorem that says that when we compare European and American call options, not puts, call options, we will always be indifferent. It's a theorem, it's a consequence of the maximal principle of differential equations. We're not going to spend any time on that, but there's a whole theory that arises from this. I am not interested in covering that, but I want to alert you that this theory exists, is very interesting, just not for this course. What I want to do is I want to focus our attention into this decision-making application of option pricing. And I want to establish a principle. When we have to make a decision, what we do is we evaluate the two options we have, to be or not to be. We find the value of to be, we find the value of not to be, we compare, and we take the path which is best for us. In the case of the American option, we need to compare the price of not exercising, which is a European branch, or the price of exercising, which gives to an immediate payoff. You compare the two and you do what's best for you. Now, these could be taken to the next level of sophistication, and that's to consider swing options, in which you have the ability to exercise multiple times, just not the same day or at the same time. These are options that originate mostly from the energy sector originally, because energy is, in the case of natural gas, we went through that. It has a volumetric limitation. So as we will see, this has impact in the value of those options. And when one participates in these markets with volumetric constraints, because of the inability of exercise many of these options at the same time, you're going to give up rights to have options which are cheaper for you. And this is the origin of this. Volumetric constraints give rise to these situations. Now, I wanted to put this in a more, I guess, entertaining perspective and more modern perspective by explaining how a Air Canada FlexiPass is a swing option. These are passes that allow the holder of the pass to, in this case, I have the New York and Boston commuter, so you can fly to New York or Boston. You can buy 10 tickets, and you can see that for an average price of $382, you can lock in that price. Of course, Air Canada does not force you to use a flight pass every time you take these flights. If the price is cheaper, you can buy a new ticket and save that for the next flight. But if you're either close to maturity or prices are higher, you have a decision to make. Shall you use the flight pass or not? That decision is exactly what we're doing today. It's exactly what we did a few minutes ago when we considered how to deal with American options, whether we exercise or not exercise. These are options that you can only exercise once. In the case of a 10 flight credits, you cannot use them twice in the same flight. They are personal, they're not transferable, so you can use them only on one flight. If one flight happens to be very expensive, you like to exercise more than one, you can't. You can only exercise one. Because of that, they should be cheaper than 10 corresponding American options. And that's what we saw last week. We also saw a variant of that flight pass for companies where up to 10 people can fly together. And we can see that in this case, this flight pass should be slightly more expensive because you can exercise up to 10 times for one flight. Still, we see that Air Canada offers the flight pass at the same price. It's not a big deal for them. This is not a mispricing situation. It is just that from our perspective, from the arbitrage-free pricing perspective, this price is wrong. This small and mid-sized business perspectives should be more expensive, just from a pricing perspective, okay? We're not getting into business issues, why Air Canada does this, or how profitable these flight prices are. Remember, we're still in the position where no one makes money. We work for free, okay? All right, so to develop the way of thinking about this, what I wanted to do is I wanted to give you the general framework in summary form of how these swing options are dealt with. It's a very interesting example of how to use exactly the same approach we used for the 33-cent game, just that we are going to do it over and over and over and over again. And that will allow us to price potentially very complicated securities. So it's a discipline of thinking more than anything else. So if we have an option, say an American option with a payoff equal to 75 cents, if we can exercise this twice, but not on the same day, then it's suddenly not an American option, it's something different. And our objective now is to find what is the price of this swing option. I'm going to denote it with the notation P2 is not 0. So 2 corresponds to the fact that I have a 2 upswing. I have 2 tickets that I can exercise. I call it S. 2. S corresponds to the value of the stock today. So today that will be 1. Okay. But if that number changes, then I allow the price to be a function of that number, and this is the time today, so that's today. That's today. These variables could change, these parameters could change, and we want to calculate that price. There were some considerations that we went through a little bit rushed last week, but I think they're easy to understand. We're going to find the price, but I want to play around with very simple considerations where we can get bounds for this price. So the price has to be more than 25 cents, because if I exercise immediately, I get 25 cents. So the price has to be more than 25 cents. It cannot be worth more than $1, because if I buy this ticket and I exercise at the, for example, if I exercise now, I will get 25 cents. If I exercise at a future point in time, I have ways of exercising this so that I get $1. So it has to be cheaper than that. But more interesting than that is the upper bound that says that the price is no bigger than 2/3. And the reason is the value of the American option is 33 cents. And because this gives us less rights than 2 American options, the value cannot be more than twice the price of 1 American option, which is 1/3. So it cannot be more than 2/3. We're going to find the price exactly, but these are considerations that we can have before we get started on that. And the way to do that is to follow our principle, exercise or not to exercise, and price our decisions in that manner. If I have a, and we start always at expiration. At expiration, when the stock is $2, if I want to know the price of a 2 swing option, there the price is $1.25. I have 2 tickets left, but only 1 can be exercised before it matures. That's why the price is the same as the American option, $1.25. You can have 2, you can have 100 tickets. It doesn't matter. The price is always $1.25 because of the restriction that you can only sell 1. And if the stock is at $1, it's the same thing. It's 25 cents, not 50, because you can only exercise one. Now, what happens the day before, or the period before? If the stock is at $1.50, if I exercise, what do I get? If I exercise, I get a payoff of 75 cents, but I have now an American option, which is a one upswing when the stock is $1.50 and is at time equals 1. And that has a value. The value of that is the value of the American option, which was 75 cents. Okay? Now, if I don't exercise, I have a European branch, because I'm not exercising, and the value of this European branch is 75 cents. So in the first case, I get $1.50 if I exercise. In the second case, if I don't exercise, I get 75 cents. So from here, we can get what is optimal. It's optimal to exercise, $1.50. And at that point, I jump from this tree to the other tree, which is the one for the American option at that point in time. There's an important footnote that I need to add here. I will add it later. I don't want to confuse you with that now. I want to make sure that this is understood. Let me continue. The way we're going to be pricing, in general, a K upswing option is it's similar to pricing K American options, but at every point in time we make a decision. Do we compare the price of a K up price and K minus 1 up price, and that difference, if the difference is bigger than the payoff, then we don't exercise, and if it's smaller, then we exercise. Again, it's exercise or not exercise. In the case of a two upswing option, this is how it all looks when I go through all of the steps. We already did that step earlier. The price was $1.50. If I go to the step below here, it's kind of trivial. If the stock is at 75 cents, so whether I exercise or not, it doesn't matter. I get a payoff of equal to 0, so the price continues to be 12.5 cents, similar or the same as in the American option. And when I get here, this is an interesting point. This is the point, the node. Now I can exercise or not exercise. If I exercise, I get 25 cents in cash, and then I change trees to the American option, and the price of the American option was 33 cents. Okay? When I changed tree, the value of the American option was 33 cents. The value is 58 cents and a third. That's if I exercise. If I don't exercise, what I get is I have a European branch. And the European branch, if you price it with a replicating portfolio, which we have here, you can find that the option is worth 58 cents and a third. It's the same as if you exercise. So at this point, you are indifferent. This is a point of indifference when we have this swing option. Today, the stock priced at $1. Okay, so the result is that we have the prices here. And more importantly, what I have is, in this case, we exercise. Here we're indifferent, and here we're indifferent too. Okay, and this completes the discussion of how we would price these swing options. Is that clear? Seems clear. I don't know. Okay. There's an important footnote, and this is now part of the sophistication of what we are doing. The footnote is this. When I change trees from the K upswing to the K minus 1 upswing tree, and I do this recursively. I start with 1, then 2, then 3. When I switch trees, it cannot happen that I switch trees after I exercise, and the price that I find in the new tree is the price that I have when I exercise again. That is not allowed. That means that we have to do something on top of this. I'm not particularly interested that you remember this, but it's important to get into account, okay? Which is, as we fill these trees, we need to maintain a database, a parallel database of the price if we don't exercise, because when we change trees, we have to go to the new tree, but we cannot exercise. Therefore, we need the price of that tree when we remove the option to exercise on that particular day. That's the footnote I need to add. This adds some complication to what we're doing. It's something which is not particularly challenging, but I just want everybody to be aware of some of these complications. Okay? And this is something you can use to price, in this case, the flight passes of Air Canada. Okay, so I'm finished with this. I hope it's clear. I would like to give you maybe 1 minute for questions. There's a question here. I apologize. I cannot read the chat while I'm lecturing. I'm too focused on what I'm saying. Okay, but now that I had this question, I see here a question from Harsh. Can you give a quick 1-2 sentence summary of the big ideas from that presentation? By that presentation, you mean this presentation, Harsh? Yes, okay.
I'll just unmute. Yeah.
Yeah, okay, so you talk about this presentation, the one on swing options or the one on decision making?
I guess both. I
Okay.
was a little lost throughout the entire thing.
Oh, okay, that's not good. Okay, so let me tell you. Let me talk about pricing decisions, which is really what we are doing. If we don't have decisions to make, it's all quite clear. We have a situation today, it could develop into situations tomorrow. And we have a way of doing that. We learn how to do that with matrices, with replicating portfolios, all sorts of ways. Okay. If we have a decision to make, then it was not clear before I gave this presentation, it was not clear how you would attack that. And the attacking that we do is very simple. I have decisions to make. So I say, make one decision. Decision number one, exercise. Decision number two, don't exercise. Each of those decisions leads to a different tree. That's what I'm saying. That's what I'm actually doing. Each of those decisions at the micro level leads to its own option valuation. That's the key. That's what we're doing. A decision puts you in a certain position. For example, you have to fly to New York tomorrow. You have a flight pass. So you exercise or not. Then what you do, don't think of what might happen. No. You are able to calculate the value of your flight pass as it is today. You can do that. If exercise one, you know your savings and you know the value of what's left because there are options. One is just cash and the other one is an option. So you know that is the sum of both. If you don't exercise any rights, any tickets to go to New York, then you have the same option extended 1 day longer, and you know the price of that too. So you price them separately and you compare. That's what we're doing.
I guess a quick follow-up.
Yep.
A follow-up to this is, I guess I don't understand like the whole like context of like European versus American. So like
Okay. Yeah,
when you said that, like did you mean that when we switched to like the other option or like the other branch, right? You said that we're in like a European branch. I don't get like exactly are we like in an American context, but then if we're like forced, then we're European? That's what I don't get.
Okay, so let me address that then. This is important and this is easier. A European option is one in which you don't have any decisions to make. And that is the 33-cent game we played at the beginning of all of this. You don't have a decision. Once you decide to play, you pay and wait for the outcome. You don't have decisions to make. In the American case, you have decisions to make, which is you can say, I exercise now. I'll give you an example of an American option, a mortgage. A mortgage is an American option, partly American option. It's actually, it's called a Bermudan option. We'll talk about that later. Why? Do you know how mortgages work? A mortgage is the bank gives you a loan, and then you have a fixed rate payment. If rates go up or down, you pay the same. But if rates drop, you're not forced to keep the mortgage. Mortgages have prepayment abilities for the holder of the mortgage. It's not that you can prepay the whole mortgage. You cannot do that. You can only prepay 10%. You may have heard that. I don't know if you have a pay 10% of the mortgage at any point in time. So that means there's some partial rights for exercise. So it's as if you have 10 options of which you can exercise one every year. You see what I mean? So that's an example of an American option. It only affects one of the 10 that you have. You can only exercise one. It would be a swing option if you want. You see? It's another example. You can only exercise one. But imagine a situation, back to my first example here, where you have a stock, it's $1 now, $1.50, 75 cents, $2, $1.50. And you buy the option, you can buy that stock for 75 cents whenever you want. You can buy it now. You can buy it now. So that right you can exercise right now and say, you know what? I will exercise that right now and I get 25 cents. Well, that would be silly because you're paying 33 cents for the option today. You're turning 33 cents into 25 cents. You're losing money. But you have the right. You could have done it today, right? You could do it tomorrow. Maybe tomorrow the stock goes to $1.50, and your option is worth 75 cents. But the payoff is also worth 75 cents. I have the option. I can buy the stock for 75 cents, which means I make 75 cents tomorrow. You have the right to exercise that right. That means you have the right to make 75 cents tomorrow if the stock goes up. You could also decide to wait. You said, no, I'm going to hold on to the right because the day after I could make $1.25. So tomorrow, if the stock is at $1.50, you really don't know what to do. You really don't know what to do. I'm going to go there. Tomorrow, when the stock is at $1.50, you really don't know what to do because you can make 75 cents on the spot. Do you understand that? If the stock is at $1.50 tomorrow, you can exercise the option and make $75 on the spot. You give up your rights for the future, you get 75 cents, or you go home and you can say, well, I'm happy. I paid 33 cents for this and I'm going home with 75 cents. You made roughly 300% return. 200% return, 200. Yes? Well, that's a possibility, but how about you wait? You can say, you know what? I like gambling. I'm going to wait because I can make $1.25 the next day and I feel lucky. Imagine you think like that. We don't think like that. We think from an arbitrage-free perspective, but you could think like that. I'm going to gamble. I'm going to hold on to my option because tomorrow I could make $1.25. And that's great. You paid a third of $1 and you're going to walk away with $1.25. That's a very big return on your money, right? But it also could go down. The stock would go down to $1, in which case you only walk away with 25 cents and you say, well, what shall I do? What shall I do? What shall I do? If you wait, it looks like you're gambling. If you don't wait, you get cash and go home. You understand that? But now we've learned that we're not gambling if we wait. Because if we wait, it's the same game as the 33-cent game. Have a stock, is worth something, it could go up or down. If it goes up, it gets something, it goes down, it gets something else. There's a replicating portfolio that says that that game has a deterministic price. We know the price is 75 cents. The same as if you exercise. It's coincidence. But we know how to value that decision. If you decide to wait, the waiting will give you an asset option, which is worth 75 cents. And we know that because we're pricing that European branch. If I don't wait, forget about the European branch, I get 75 cents in cash and I walk away with the 75 cents. Do you understand that? Waiting means European. You've decided not to exercise, so that branch is European. European is that you let the coin flip happen, so to speak. We know that the coin flip is the wrong analogy, but it's a figure of speech. Yes? Tomorrow, this could be part of a very long sequence of ups and downs of the stocks. The day after, maybe you don't get $1.25 in cash. This is part of another option that who knows, you can exercise or not. But we know it doesn't matter if you have an asset which is worth $1.25 because the game goes on, or you get $1.25 in cash. We know it doesn't matter. It's the same to us. So that is the approach that we are taking. This turns into this game where if we are here, we need to decide what it is. And if we exercise, that's what we get, 75 cents payoff. And if I don't exercise, I get the 33-cent game, which is a European option. I'm indifferent because both happen to be equal at 75 cents. That's what we're doing. And what I told you about the swing options is the same way of thinking, just with a higher level of sophistication. But at the end of the day, this principle is the same. The principle still works. You have to do it many more times. You have to do it recursively, starting at the beginning with very few exercise options left, and then increase, go back, and then increase the number of options, and then you price the trees for all possible decisions under all possible scenarios, under all possible days going to New York. Is that more clear?
So basically what you're saying is that like this is just we're just checking out like if we want to like exercise the option or not, and like this is just like terminology in terms of like I guess what like people in finance call it.
Yes.
Okay. And then in the case that we have like a really big tree, because this one only has like 2 days worth, right? Then we would have to like go backwards in terms of like from the.
You always go backwards. You always go
Okay.
backwards. And why we go backwards, it will become more clear next week. Because once we go to, now we're doing what, 3 time steps? This gets crazy very quickly. In Python, no, you can write Python code, which is very easy. But this gets crazy very quickly. And instead of explaining what happens if I say 6, I'm not going to do 6. I'm going to do infinitely many. It's easier to understand. And that's what we're doing next week. I'm just now going to give you what you need to know about stochastic calculus so that next week we are ready to do this, not 2 times, not 3 times, but infinitely many times. And then it'll become even more clear why we have to go back. We always do it by backward propagation, just like neural networks. And there's a reason why. It's the same reason as neural networks. That's why you do backward propagation. Why? Because there's a point in time when I know everything. In this case, it's at maturity. In the case of neural networks, is when I know the answer, when the answer is revealed to me, right? In the case of neural networks, I'm fitting my network parameters to the answer. In the case I'm not fitting anything, this is deterministic, completely deterministic. I happen to know what the option is worth at the end, and then because of that, I can know what the option is worth 1 step prior to the end. because it's just a collection of 33-cent games. And then one step prior to that, because it's another collection of 33-cent games, all the way to today. So the concept of backward propagation is the same as a neural network as it is here. It's because I know the answer at the end. The process is different. In one case, I'm trying to optimize parameters. In this case, I don't need to do that. In fact, unlike neural networks, which don't have a solution, you just find the best fit. Here, the answer is always exact. But you have to go back. You have to do backward propagation. And in the case of swing options, not only you have to do backward propagation, you have to do backward propagation mixed with jumping trees from one tree to another. Because exercising a ticket going to New York means now you have a different swing option with one exercise right less. If it was more, I would be in trouble because then I don't have a clear induction process. But because it's one less, okay, so I start with few and then I build up with more and more and more and more and more. That's why in this case backward propagation also works. In time and in the number of options I have left to exercise. Okay? All right. See, I remind you, what we're doing here is we're only looking at the landscape. I'm not developing these concepts. This requires a whole new course. I'm not doing that. Some of you may need to do this. Some of you may need to learn more about this. I suspect that at most 2 of you will have to know more about this. Fine. When you do that, remind my words, watch the video again, and then you'll be prepared to get into this vast area, which is pricing all of these exotic options. The path I chose to continue with in this course is slightly different. The path I continue to follow is the path where I'm going to get more and more and more exercise points as opposed to increasing the complexity of the options that I have to deal with. Okay? Okay, I hope this was clear. All right, any other questions? Eve?
Just a quick question, kind of related to the example you brought up about mortgages. If it was a variable rate mortgage, how would that kind of change things in this
Okay.
case?
So a variable rate mortgage is not an option, right? Because you're not, how can I say, if rates go up, you pay more. If rates go down, you pay less, and that's it. If I can put that into the context of options, is in a certain sense, let me draw on. So yours is a good question. Let me draw on an analogy. A mortgage. Think of a mortgage as a futures contract. Okay, where you're guaranteed to a rate. If somehow the rates get cheaper, you still have to pay. So you say, damn, I should have gone with a variable mortgage, right? So it's like a futures contract because the market can move against you. In the case of options, they don't move against you, right? They only move in your favor. You pay the premium, but then they only move in your favor. So you could argue that a fixed rate mortgage is a futures contract, not an option. And a variable rate mortgage is you just pay market price, so that's it. Okay, there's no optionality in the variable rate mortgage, except for one thing, which is that the fixed rate mortgage, it has an optionality built into it because you're not obligating to pay the full amount if rates go down. You can prepay, and the prepayment ability is the option embedded in that mortgage. It's not a full option. You can only prepay 10% of it. So the way to model that is as 9 futures contracts and 1 call option for the full amount of your mortgage. And that's how you would price them. So I think that's a good question, because if I bring, so I did the summary for Harsh, now you have a question. This is interesting. We're talking about, at the beginning, we talked about options and we said options this, option that. But now I'm talking about everyday things like mortgages. I don't know if any of you has a mortgage, okay? But mortgages are there. They're around us. People around you have mortgages. And flight passes are there. You can buy them from Air Canada. Both, both are dealt with exactly the same way, which is by this way of thinking, which is very micro-local. We make decisions and we realize every time we make a decision, we have an option, and the option or equivalent. A futures contract is easy to price. We saw that earlier, right? It was easy to replicate a futures contract. You borrow and you buy. The option is the one that is more difficult to price. So the mortgage, the complicated part of the mortgage is the optionality, it's not the futures component. But the engineering we're learning here is that you take whichever instrument is given to you, mortgage, flight pass, you decompose them. And once you decompose them, they're going to be a combination, they're going to be a portfolio of futures, stocks, bonds, options, this and that. Each of them can be priced separately and then you put them together. And that would be a very good way of thinking about a mortgage. But a floating rate mortgage is not an option. Okay, it's you just pay market price. It's not even a futures. You get no protection there. Great. Okay, so actually, well, this I think was a good discussion. Like I said, well, now we need to take a break for two reasons. One is because I need to change to a different deck, and we've been talking now for almost an hour. So let's take now a 10-minute break, and when I come back, we'll start with something completely new. So this can be viewed as another episode in our saga, but this episode is now complete. It's going to be very different. We're going to have to bring a lot of considerations into account. But I want to start with one story. This happened in this course, I'm guessing almost 30 years ago. That was at the beginning of this course. And it's a story which I like to use to explain how this happened. I think you will identify with this story. There was a story of a student, a very good student, that when he heard this presentation we just finished, he thought, this is great. He went and very quickly did a program to calculate the option price with an increasing number of trading days, an increasing number of values. So you get, we've seen a tree, which is 1 goes to 2 goes to 3. So you can do this for every day for a year. You can go then to every hour, doing every minute. You can write code. This was before Python. Python didn't exist back then. He didn't see, I think. But you can write code. You can write code that implements everything we have seen so far, right? You can see, can you see yourselves implementing code of what we've seen so far? Yes, you can. Okay, I'll give you actually the context. Okay, so we have an option like the ones we have seen before. You don't know the price. Okay, you have the stock, you know the price, and then you go one branch at a time. You get a replicating portfolio. You jump to the other branch, you get a new replicating portfolio, you get the price, and then you go to today, and then you get the replicating portfolio, and you get the price. You can do this. You can implement this in Python, okay? I'm sure you can. So this is what he did. He codified each stock movement from one day to the next, considering a percentage increment equal to 1 plus or minus a number u every day. So it goes up by u%, down by u%. Okay? You see that. And then you can run this through time. It gives you a tree. See that? He knew that another possibility would have been to model the price tree slightly differently. Instead of multiplying by 1 plus or minus u, you can say I multiply by 1 plus u, or I divide by 1 plus u. It's not exactly the same. It's similar, but it's not exactly the same. You could have done it like that too. Are you following me? I would like everybody to be in a position to say, yes, maybe some of you have already done it. I would not be surprised that some of you have already tried this. Yes? So say, well, this is how I want to price my tree, and I can do this for a variable t that goes from 0 to a million, or some hard-coded number, capital T or something like that, equal to a million, okay? Being a good student, he knew that both models are approximately the same, and he was right. You know that by Taylor expansion, multiplying by 1 plus u to the minus 1 is similar to multiplying by 1 minus u. The difference is of the order of u squared. And if u is a small number, u squared is negligible. Following me? He did not care to make u time dependent or dependent on other things. So u is just a number. That was also a good choice. This was his first attempt at doing option pricing in continuous time. He picked a 1 time year horizon, also a very good choice. Are you following me? So you pick a user-defined number. N is the number of steps, number of days, number of time steps your tree is going to have. Another good idea. All these are good ideas. And for you, he thought correctly that the value should depend on the stock volatility. So stocks which are more volatile will have a bigger U, and stocks which are less volatile will have a smaller U. Also a good idea. So he coded U equals to sigma divided by N. So when N is the number of steps that you have, more and more and more, then U becomes smaller and smaller and smaller. But it allows for a variable sigma that if the volatility of the stock is higher, you have a bigger spread at every one of these infinitesimal steps. Are you with me so far? Are you following this? I think I would get that most of you, if not all of you, could write Python code for this. He did it in C. There was no Python back then, but you could all do it, right? Okay. So the way to code the option price is for each branch, we give a probability of a half of going up or down. And that's because the value of the stock today is 1/2 of the value of stock tomorrow. If it goes up, plus 1/2 of the value of the stock tomorrow, thank you, Ariel, if the price goes down. And then from there, we can do the backward propagation by pricing the option price as the average of the values tomorrow if it goes up, and tomorrow if it goes down. And recursively, this will give us the option price today. And we can obtain the replicating portfolio also very easily with all of that. Now, this is the problem that he encountered. He wrote the program very quickly, a day, okay? And was excited and run it and see what happens when n goes to infinity. What do you think happened? It did not converge or converge always to 0. He thought there was a bug, looked around, looked everywhere. No, everything was correct. Do you know what's going on? Anybody knows what the mistake was? Yes. Yes, Arya.
Is it because you average out, like when you have equal probabilities for it to go up and down, like if you take large numbers, it would average out to like an average of 0?
No, that was the right decision. Yes, a half chance that it goes up or half chance it goes down is still okay. Still okay. Let's review the central limit theorem for a minute, okay? You probably know the central limit theorem, but I want to put it into this very practical context so you see the implications of that. Okay, so let me tell you the important dimensionality constraint that we need to have. I'm going to give you the answer, how it should have been done, and then I'll explain to you why with the central limit theorem, okay? Okay, so I'm going to work with the variable, which is the logarithm of the price. When I take the logarithm of the price, when I multiply by a number, it's as if I add something to it, okay? So that means that x, which is the logarithm of the stock price, will be the logarithm yesterday plus a number. And the number is plus or minus u, very closely, plus or minus u. Are you following me? Great. So now what we have is that the logarithm, as I take all of these many points, is the first value plus the sum of these coin flips t times, where each of these coin flips has a mean 0 and a standard deviation of u. I remind you, we took u to be sigma divided by n, capital N, where capital N is the number of days in the year that you're simulating this. Are you all with me? What I've done, I've taken logarithms so that the multiplication of the stock, this geometric equation, turns into an arithmetic equation. That's all I have done. I'm modeling the logarithm of the stock. The stock is never negative, so I can always take the logarithm. Okay? And this is the expression that we have. This expression that we have here this expression is the key. What does this expression do? We apply the central limit theorem to this expression to get what? According to the central limit theorem, this will converge to a Gaussian distribution with mean x naught. They are coin flips, the average is 0. But what's the standard deviation of this? The standard deviation of this is u, the individual standard deviation, times the square root of the number of coin flips, square root of n. See that? The standard deviation is not n, it's not t, it's the square root of n. Do you see that? This is the central limit theorem. Anybody does not know the central limit theorem? Are you familiar with this? This is the steepest part of this climb today. I need everybody to remember this. When you take n coin flips, the standard deviation of the sum is not n, it's the square root of n, if they are independent and identically distributed. The standard deviation grows like the square root of the number of throws, not like the number of throws. The mean grows like the number of throws, but not the standard deviation, that grows like the square root of the number of throws, because this holds the answer to the mistake he made. Anybody sees the mistake? He had scaled u like sigma divided by n. It's too small. U should scale like 1 over the square root of n. If you write that computer program, it will not work. I think this is the best way to explain how we pass to the continuum, to use this example. You can try this yourselves. You can write this Python code with u equal to 1 over n or some constant divided by n, and you will see that it doesn't converge. This is a random walk that we're doing. This is Brownian motion. If each time step, if each infinitesimal coin flip, you move only 1 over n, you're moving so little that you never leave the origin. The limit when n goes to infinity is you don't move. The price of the stock doesn't move. You're writing a very complicated code to simulate no movement. Understand what I'm saying? The central limit theorem tells us that the only dimension for the size of your steps is 1 over the square root of n. Mind you, 1 over square root of n is infinitesimally large compared to 1 over n. 1 over n is very, very small. 1 over the square root of n is the right amount. And that n to the power minus a half, you cannot touch. You cannot make it bigger than minus a half, smaller than minus a half. The only way for this algorithm to converge is if the step is exactly proportional to n to the minus a half. Do you see that? This is the magic. That's the important thing that I want you to remember. If you remember this, you'll understand everything. The fix was very simple. You go at the beginning of the code where you wrote u equals sigma over n and changed by sigma divided by the square root of n, and everything works. You've taken courses in probability, you've taken courses in stochastic processes, and maybe you already knew this. Maybe this is not a surprise. Maybe this is not a surprise to most of you, but maybe this is a surprise to most of you. And this is a very good example how when you write code, you need to know what you're doing. The math will dictate how you write your code. You write it wrong, you're spending a lot of work modeling the number 0. Sometimes you're spending a lot of time looking for something that doesn't exist. That happens too. Okay? All right. So we've done this steep climb. From here, I can go back and I can give you the theory and it all works and this night, but I still would like for this example to sink in. I think you've put yourselves into the mindset of a student trying to implement this quickly. And what happens at the end of the day when you do that. So this is the way to do this. This is the way to now do this from the beginning. Let's say that we're going to do coin flips. And when you do the coin flip, you decide if you go to the right or to the left. And I'm going to take the following dimensions. If I flip heads +1, I always go forward. So my dx always goes forward, or my dt always goes forward. But if I flip a +1, I take a step to the left. And if I get a -1, I take a step to the right. That's what I'm doing. I'm taking steps. And the jump, when I take my steps, I call it dy. So I have dy and dx. Dx represents time, dy represents size. In this case, it's a random walk. This is not a very good representation of stock prices because this allows stock prices to become negative. It's a good representation of the logarithm of stock prices, but it's also a good representation of, for example, how viruses spread. Right? And you know that you probably know, this is called Brownian motion because this was introduced, not really discovered, but introduced by a botanist, Robert Brown, when he was studying the movement of dust and pollen and things like that. And it was quoted by Darwin in his Origin of the Species book. And that's what was called Brownian motion. Goes back to the work in the 19th century of Robert Brown. I think 1820 something is when he wrote his book on this. And what we've learned is that the dimensions dy and dx are very important to each other. In traditional calculus, dy and dx are proportional to each other, and the proportionality constant is the derivative of your function. In this case, dx and dy are not proportional to each other. dy is proportional to the square root of dx, and the proportionality constant is the volatility. Okay? So we need to revisit calculus all over from the beginning, because everything we've learned in calculus does not work in stochastic calculus. It's completely different. Now, I'm not going to give you a course on stochastic calculus. I'm just going to tell you how to get to the answer we want in such a way that you develop the intuition. And if you want to know more, there are countless great books that explain this to you. Okay. And yes, I am not going to explain this theory. I'm just going to tell you what it means. That's the principle of this course. So if I have a number of random walks, the central limit theorem will tell me that as n grows, this sum converges to a certain limit. So I'm going to take infinitesimal steps, which are of size dx on time and dy in space. And because I will get to the value of this sum, I need dy and dx to have a certain proportionality. And that's, here is the central limit theorem. The limiting probability of the normalized value of my sum is the Gaussian distribution, which forces a relationship between dx and dy. dy is proportional to the square root of dx. Then we have convergence to a normal distribution. Otherwise, we don't. Otherwise, we don't. We converge either to the trivial distribution or to a distribution which blows up in 0 time. And what you have in the graph down here is how the results of all those many graphs are. When you take many possible graphs here, all with a certain probability, the result is the Gaussian distribution that you have there. Okay? So this is the central limit theorem in our context. I'm going to assume that this is well understood. Now, before I move on, I want to see if there are any questions. I'm about to tell you Einstein's perspective on this. Any questions? No. Okay, so Einstein in the year 1905 approximately wrote a very interesting paper where what he did is he had a probabilistic approach, random walk approach. The word Brownian motion was not really coined yet. Two diffusion processes. And the argument I'm going to give you is if I have a heated one-dimensional rod, I want to show you how temperature evolves over time. I know that many of you, probably all of you, have seen this equation. It's called the heat equation, and you probably saw the traditional derivation of this done by D'Alembert and others. I'm going to give you Einstein's derivation, which is most relevant for what we are doing. Okay? So this is by U, I denote the temperature of my object. The temperature, U is the temperature. I'll take this here. It's the temperature. X is the location of my rod, and T is time. And in the simplest situation where your material is isotropic, isotropic means that temperature moves to the right and to the left with the same probability. So there's no particular reason why the temperature wants to go one way or the other. So from an isotropic perspective, the temperature tomorrow here is going to be 1/2 of the temperature in the neighboring particles, whatever that means. You want to read the real paper, you read Einstein, but I want to do this in one page. I want to summarize Einstein's paper in a single page. Another gross oversimplification, which is now becoming an element of this course. Einstein paper in one page. Actually, in one picture. You understand that? The temperature in this particle is 1/2 of the temperature in the neighboring particles. There you go. You can verify that's what I wrote. That the temperature here tomorrow, well, infinitesimally tomorrow, is 1/2 of the temperature now, a little bit above, and the temperature now a little bit below. Right, let's do some algebra now. Let me here subtract uxt from the right and from the left. That's what I'm doing. I'm subtracting uxt. See that? Great. So let's gather all of this. And what I have on the left is the partial derivative of u with respect to t. And what I have on the right, you recognize here perhaps the discrete second derivative of u with respect to x. On the left is the derivative times dt, and on the right is the second derivative, second discrete derivative, times dx squared. But dx squared is like dt. Right? So the two kill each other, and you have the heat equation. See that? This is Einstein's paper in one picture. Okay, so let's put this to work. When we do random walks, now we're climbing our mountain again, okay? So in the passage through continuum of a discrete t, we have a very important dimensionality constraint, which is that a tree is going to behave like a random walk with infinitesimal coin flips, with mean zero and a standard deviation u, which we know has to have a precise scale, which is 1 over the which is the square root of the number of throws that we have, or 1 over the square root of dt. If we keep my time window fixed, say 1 year, then u should be like sigma over the square root of n, and t should be like 1 over n. The central limit theorem is what tells us that this has to be like that. So we have this fundamental relationship, which is that the infinitesimal change in price is proportional to the square root of time. And this allows us to build what's called Ito processes. Now, Ito processes, and I know that in doing this, I have another gross oversimplification in this course, is called dx, that's my Ito process, is mu times dt, that's what's called a drift. I'll explain this in a minute, okay? Plus sigma times dw. Now hold on, let's look at this equation with some detail, okay? This is very important. So this was done by the mathematician, Japanese mathematician Ito. And what he was doing was not looking at stock prices. His original motivation was the movement of boats at sea. So boats go in a certain direction, that's the drift, but then they get moved in random ways by, for example, water waves. Right? So you know ships cannot move with precise accuracy. There's always some randomness. So he said, well, the way to model that randomness is exactly this one. So we talk about boats, as you're moving, that's your deterministic. That's your deterministic motion given by the direction the boat is moving, maybe by the engine. Right? And this is the randomness that you cannot explain, that comes and goes, takes it to the right, takes it to the left. We know how to model that now. We know how to model that now because we just did it. This would be sigma essentially over, sorry, this would be sigma times the square root of 1 over n plus or minus. That's the movement that I'm going to have here. So this plus is plus minus because this is a coin flip, an infinitesimal coin flip. But this is of the size, and listen to this, this is important. This is mu 1 over n. 1 over n here, 1 over square root of n there. The randomness has to be much, much bigger than the drift. If the randomness is of the same size as the drift, you don't move. The boat will go with precision as if it's driving on the road. We need to introduce the randomness, which is infinitesimally large compared to the deterministic nature. So this is, and I'll be with you in a minute, okay? So if this is traditional calculus, Newton. This is stochastic calculus. So this is the stochastic part, and this is the traditional part. Yes, there we go.
Yeah, I just had a question. When you said that sigma plus square root of 1 over n is like the volatility, how does which part of the equation does that relate to? Because you circled the plus sign and you said it was a plus or minus. I'm just a little bit confused by that.
Yeah. Okay, so this is an infinitesimal coin flip, okay? It has a probability of 1/2, so 50% chance that you get plus a square root of 1 over n, and 50% chance that you get minus 1 over square root of n. Either this or that.
Okay, so like the dwt is the square root of 1 over n.
Yes.
Okay.
Yes. So dwt is like 1 over the square root of n. But dt is like 1 over n. So dt is very, very small, and dw is very, very, very big. Right? And that's very important. Why? Because in this movement, again, it's the central limit theorem, there's cancellations when you go to the right and to the left. And if the movement is like 1 over n is so tiny, these cancellations will kill your movement, and then you are with absolute precision, you're driving on a road. The random movements have to be infinitesimally large compared to your deterministic movements. If randomness is the same size as your deterministic little steps, in the limit, the randomness disappears. That's what I'm saying. And this is a very interesting blend because you have traditional calculus and stochastic calculus in the same equation. That's what I need to process is. It blends the stochastic nature and the traditional calculus nature into a single equation. All right? And the rest of the day will be devoted to learning stochastic calculus. We're almost done, by the way. If you have questions, stop me, because I have plenty of time. I cannot lose anybody here again. Okay, there are times when it's okay, but now I don't want to lose anybody. So the drift term adds an infinitesimal deterministic direction to the walk at each step of very small size. Dt is very small. But dw adds a very large stochastic side to the right or to the left with probability half. Very large. I use the word or the term W, not B. Sometimes people use DB. B goes for Brown. I use DW, not Brown, but Wiener, Norbert Wiener, early 20th century, because Brown was a botanist. He came up with this model, and the model was made mathematically precise by Norbert Wiener. So when you write mathematically precise equations, people tend to write the word W for Wiener. And when you write models which are not precise, people tend to write B for Brown. You will see that I changed back and forth from one to the other. I never know which one I'm using, okay? And there's a chance that I could make the occasional mistake that I write W here and B on the next line. That could happen too. I try to prevent it, but it's hard to avoid because B and W are used interchangeably. They did their work about 100 years from each other. One was mathematically precise, the other one was not. In fact, during the time of Brown, mathematics was not mature enough to make those theories mathematically precise. It was impossible. You couldn't do it. Okay? Math had to go through a growing pains to create probability spaces and very new material done around the turn of the century, around the time that Einstein did his paper, and then Norbert Wiener managed to get the formalism of that shortly after. That was almost 100 years. Not too relevant for us, but interesting historical comments. Ito processes can be very complex, with mu and sigma taking functional forms. They can depend on many variables and this and that. They can depend on X also. We're not going to do that here in this course. Again, if you want that, there are entire courses devoted to developing that. I'm happy that you understand the relationship between the size of the randomness and the size of the deterministic steps that we take. We will use them for securities, but they're used to describe many other processes in nature, many other processes. Well, we started with pollen and dust. This is what Brown was doing. Okay, so on the basis of this, we can create a stochastic calculus. And a stochastic calculus is going to use a fundamental object, dw, which I'm happy to define it as a random, as a coin flip of size dt with probability a half that goes up and a half that it goes down. And that's all I'm going to do. I'm not going to give you any more formalism. If you want to know more, then take a different course or read a book. Okay? That I'll be happy if you know that. And this is what results in the random walk that has a marginal distribution probability, which is a Poisson distribution. Sorry, a normal distribution. So my possession distribution is given by a normal distribution, a Gaussian distribution. Okay? How are we doing with the level of comfort that we have with this? Okay, Harsh is okay. Yeah, you're all good? Okay. That's my Gaussian distribution. Okay. So we've climbed this hill. Let's see what we can do with it now. Okay. Now we're going to pause for a minute. We're not going to develop anything new. We're going to see that this thing we have is very useful in the modeling of stock prices. And that's the next thing that I want to do. I want to move away from boats and other considerations, or even the heat equation, and talk about stock prices. So for stocks or many other securities, we're going to model not the price itself, but the logarithm of the price. There's a reason for that, which will become clear in the next half hour. And the stock the logarithm of the stock price will follow an Ito process like that. It's going to have a drift and it's going to have a stochastic term. The result is realistic in different ways. It's also going to be unrealistic in some others, which I'll tell you, okay? So let me focus on the realistic characteristics of this. First, the price will always be positive. It's the price, as you will see, is the exponential of x. So whatever x is, s will be positive. It's the exponential of something. That's good. Stock prices cannot become negative. There's an interesting legal reason why stock prices cannot become negative, but I may tell you later. I don't want to spend time on that. It's a very interesting legal reason, okay? Goes back to maybe 300 years. Another thing which is good, it makes the changes in price proportional to the value of the price itself, which is also realistic. Stocks which are more expensive, they move more. The stocks which are cheaper, they move less. Okay? So that's realistic too. There's some things which are not realistic, which is because of the Gaussian nature of the price, the logarithm of the price, we don't see very big moves as often as they happen. Large moves happen more often than this model predicts. So for risk management purposes, for example, this is not going to be the end of our considerations. We need to have other ways of modeling that. When we talk about risk management in a couple of weeks, I will introduce some other considerations, but for now we're very happy with this, very, very happy with this, because this is the generalization to continuous time of the trees that we saw earlier in this course. So the question I want to ask now is, if s is the exponential of x, is s an Ito process itself? You will see why this is an important question, okay? It's a very, very important question. I'm expressing this question in mathematical terms, so we all understand it. But the consequences of this question are very far-reaching. Is S an Ito process itself? We know it's the exponential of an Ito process. In other words, its logarithm is an Ito process. But is S, the stock price, an Ito process itself? And if so, which one is it? I'm not going to take votes, okay? I want to just pose the question, but now I want to pose this question in a slightly more general form, which is, in general, if I take an Ito process and I apply a function to it, a smooth function, as nice as it can be, is the result also an Ito process? This is important because if I have an Ito process and I do observations on it, observations are going to be given by a function. And I want to know if that function will also be an Ito process. You will see this is going to have very, very important consequences in what we're doing. Which one is it? So I'm about to answer that question. I will do it it's going to be perhaps easier to do it in general than specific just to the logarithm. Just note that what I'm going to do will work for stock prices by merely taking the function f to be the exponential function. That's all. But I want to answer this question. There's a hidden price in answering this question. Okay? So let's now think math. I know I have not defined any of these terms, so why do I say math? Well, I'm abusing the term math now. I know that, but that's okay. You stay with me. You will understand. Okay? All right. So for that, I'm going to do Ito's lemma. Ito's lemma is the stochastic version of the chain rule. You saw the chain rule in calculus a few years ago. Well, when we're doing stochastic calculus, there is also a chain rule, but it's different from the one that you know. And it is actually called Ito's lemma, the same Ito that invented the Ito process, the same Ito that was studying the movement of ships at sea. Okay? So, let's look at this expression. I know this expression is very big, okay? You've seen worse expressions than this one, but let's spend time looking at this expression because I want everybody to understand all of it. It's not that hard. That's my X is my Ito process. We have it there, we keep it there. We don't need to look there. We only look there for reference purposes. What we do is we look at my function and how my function moves through time. What I have here in black is what you would normally expect when you have the traditional calculus. This you would recognize is the chain rule for functions of two variables, correct? Just that part, correct? Just take a look. I want everybody to be convinced that what you have there is the chain rule for functions of two variables. If x was a differentiable function, if this was traditional calculus, that's what we have. But this is not traditional calculus. In fact, if I use traditional calculus, and allow me to do this exaggeration, but it works. There's this term here that I would have to add also. This is part of my Taylor expansion. Now I'm not doing the chain rule, I'm doing the full Taylor expansion. I'm including one more term in the full Taylor expansion. There are more terms. You're going to see that the other terms don't matter, but this one does. Everybody recognizes this is part of the Taylor expansion of my function f. You don't see this in the chain rule for traditional calculus because for traditional calculus, this element is negligible. But for us, this term is not negligible because this term is at what size? What's the size of dx squared? Dx was like dt. So dx squared is like what? Is dt. It's very important, cannot be neglected. In fact, not only cannot be neglected, but this thing, you see, gets here, gets absorbed into the dt. See that? So in the dt, I have that. Of course, I have this, goes here. But then dx, because it has this, then there's that there too. So these are the three components that the drift has. F has three elements in its drift term. The one coming from here, the one coming from here, and the stochastic one coming from here. This is the important one. And then I only have this term here, which gives me the stochastic part here. And that's it, there's nothing else. But see, Ito's lemma gives us a kind of chain rule. It's a chain rule, but has some unexpected term, the one in red. So the answer is yes, f of an Ito process is an Ito process. The stochastic part is what you expect, but the drift has an additional element in it. It's this one. It's the convexity of f with respect to the Ito process itself. When the convexity is positive, you pick up drift. And when the convexity is negative, you slow down. Let me tell you a related physical fact. This is the reason, this equation here is the reason we have no smoking laws. If it weren't for this, you just take the smokers in a room, ask them to sit in a corner, and the smoke will stay there. If you've noticed how smoke goes, you will see that it's there, but then suddenly gets a little bit of volatility, and then it drifts. Then it stays there for a while. Volatility induces drift. And this is the simplest way in which that effect appears. This is volatility induced drift. It happens in nature, okay? It happens to stocks too. And that's because dx squared is dt. Is everybody with me? Is everybody with me? I really want to give it a chance. Alex.
Hi. Wait. So I'm just wondering. Is this like similar to the thing that we did on the assignment, where it's like, like. Sorry, I don't know if I can actually talk about this assignment. I don't think is it even due yet? But like, when you're talking about like the random like motion, is that like similar to like also like the bonds and stuff?
Okay. Good question. Simple answer, no. You're not doing anything really stochastic calculus in your assignment because you're taking daily increments. However, the randomness always is there. You're taking daily increments. If instead of daily increments you took monthly increments, the relationship between the randomness that you see on daily observations and the randomness you would see in monthly observations is not 30 times bigger. It's different. So there's a time element for the randomness, which is given by this. Okay. So although this happens in the limit as the number of observations goes, to zero, the thing is that when the observations go to zero, you don't have the chance to recalibrate your analysis. In your assignment, if I asked you to observe prices once a month for the 3 months that this course takes, take 3 observations and do the run, you can do it. And you don't need to recalibrate. You're going to get different numbers. But if you're taking the limit when t goes to 0, then you don't have a chance to recalibrate. You need a model that will be consistent as t goes to 0. And that's where we have to be very, very specific about the size of those, the relationship between the drift and the stochastic term. Is that what you're asking?
Yeah, kind of. So I guess I have one more follow-up. So I guess it's like the thing about the eigenvalues and stuff. I'm not sure if I should be like talking about this right now, but like I remember like after doing some research, it was like I think it's like intended to be like something like the first component is like it's like it kind of like the thing that you said about the sine function.
That's right.
Is that like similar to like this type of motion or like this like stochastic calculus stuff because it's like kind of like it's kind of like also just like random movement of the bond, right? Or
yes.
bond.
So yes, so the randomness that you observe on a very small scale is very large. But over time, that randomness gets muffled. That's another way of expressing what we're saying here, right? If you see the effect of tariffs in the stock market today, it's very big. But then something else will happen that will move the market the other way. And then when you observe these things over time, you don't see them. They get to be washed away. There is a time element of uncertainty. And that is another way of reading the meaning of that square root term. Okay. I know that what I'm doing is, I'm not saying it's hard, but it's a gross exaggeration, a gross mathematical exaggeration. I'm using some terminology. I didn't explain what it is. In that review that I mentioned on the first day, it got one student, math, couldn't understand this. I know, that's the price I pay for doing all of this in 3 hours. I still think the benefit of time is worth it. So, and if anybody needs to know the actual derivation of this, which has nothing to do with what I'm explaining, you have to go into stochastic integrals, develop whole theory, and then you'll get it. And then it'll be proved in mathematical way, completely rigorous, not like what I'm doing here. But this has a certain amount of intuition that will be very important when we deal with security prices. My hope is that everybody is understanding this at the intuitive level, not at the formal level, of course. The formalism of this is actually quite daunting, but the intuitive aspect of that should be clear. Think of infinitesimal coin flips with huge outcomes. Okay? Okay. So from here, we can apply Ito's lemma to the logarithm of the price process. Again, this is the Ito process for the logarithm of the price, which means if we apply this to the stock price, this is the result. I'm just applying Ito's lemma blindly, just plugging in the formula to see that the Ito process that the stock follows has two differences with the Ito process that the logarithm of the price follows. The first difference is that both drift and volatility are proportional to the stock price. We are not surprised by that. That's what we expect. But the stock price has picked up drift. That's unexpected. And it's because the exponential function is convex. The stock has picked up drift. You can think of this as volatility-induced drift. So this is for the stock price process, which we'll typically write like this. And there's a very interesting application of that, which this is an example. We will see this example later. I say recall. You will have to recall in a few months, but I have a very interesting calculation here, which is imagine you have a fund which has $1 value today, $2 next month, then drops to $1, goes back to $2, drops $1, goes to 2. It just goes from 1 to 2, 1 to 2, 1 to 2, 1 to 2 every day. Every month. You see that? Okay, so let's calculate the return of this fund. This is fun. This is interesting. What's the return of this fund? Well, the first month has a 100% return. The next month has a minus 50% return. Then a 100% return. Then a minus 50% return. On average, it has a 25% return per month. Right? What if I didn't show you this example, and I'm trying to sell you an investment. I said, would you invest in a fund that has a 25% return per month on average? Would you? Well, I don't know what you think. You've seen this example. But if you didn't see this example, maybe you say 25% per month. That's a lot. I'd love that. I double my money, more than double my money every year, right? No. No. You don't double your money. You actually don't. You're not making any money. You can think of this as an artifact of accounting. and the fact that average returns don't really have the meaning that people think it has. Mathematicians know, but maybe intuitively you have that. So the problem with this example is the problem at the intuition. Many people think that there's something wrong here. There's nothing wrong. This is Ito's lemma at work. Because if you look at the logarithm of the price, what's the return? The return is 0. Right? The first month, you have logarithm of 2. The second month, negative logarithm of 2. So plus 69% minus 69%. The average is 0. But what's the volatility of the logarithm of the return? If the logarithm of the return is your Ito process, what's the volatility? 70%. Right? You see that? The volatility is 70%. What's 70% squared divided by 2? What's 70%? What's 70% squared divided by 2?
25%?
Sorry?
25%?
25%. You see? This is Ito's lemma at work. You are a mathematician, you're mathematicians. So if someone tells you, I have an investment which has an average, 25% return, the next question is, yeah, I've seen that. What's the volatility? Oh, it's 70%. You say, okay, thank you. I'm not going to invest. I don't make any money. This return is volatility induced. Not real. Well, it is real. It's here, it's calculated, it's in front of you, but it's induced by the volatility. The logarithm does not have any average return. So if the logarithm doesn't make money, the stock doesn't make money. Okay? I don't know how you feel about this. I mean, I'm lecturing online. I have but I hope this is catching on. They are different. The logarithm and the return are actually different. And that's Ito's lemma right there at work in this case. Okay? This is not a Gaussian fund. This is discrete. And it's actually far from Gaussian, but still being far from Gaussian, the prediction of Ito's lemma is quite impressive. Okay. All right. So I don't know. This was a lot for a day. I know that. Okay. And I don't know if I should continue to. This thing that we did, we're going to use that in a fundamental way next week when we develop the Black-Scholes theory. But there's some things that I want. This is a very good point to bring up something that I always like mathematicians to be aware of, which is the concept of financial false friends. The world of finance is full of false friends, things that look one way but they are the other. Okay. And I think I've mentioned to you in the past, but now it should become very clear after this example, that one of your best tools when you're in the world of finance as mathematicians is your ability to detect nonsense. Sometimes you detect nonsense and there's nothing you can do about that, right? You cannot convince anybody, but at least you are aware that some things are nonsense. And that's a power, okay? That's a superpower you have. I want you to be aware of that. You can detect nonsense better than most people. And the ability for math to discover new things is typically overplayed. I can tell you that in my experience, I have had mathematics to be more often useful to detect nonsense than to actually find new things. It's rare when you can find new things. Sometimes you do, and this is wonderful. But on an everyday job, you're going to use mathematics to avoiding false leads. Okay, to say no, I'm not going to continue that way. It doesn't work. But look, this chart is great. Look, no, this chart means nothing. It's just numbers. You understand what I'm saying? Okay. So what comes next is the Black-Scholes theory. And you tell me, shall I start that now? We have still about half an hour of scheduled time. But I know that what I've done today is very hard to swallow. I know that. I know that. So maybe I have a proposal, which is, well, first I see if there are any questions. If there are no questions, I have a proposal which we take a small break, have a coffee, or something with caffeine would be good. Come back, and then I'll do a little bit. We'll see how far we go. Okay, I don't want you to get lost, and certainly I don't want you to have the wrong feeling that this is something which is, landed on. I want you to understand it. Okay, and then next week I can start exactly here again and redo it again. How's that? Okay, we're going to do that. When we come back, we're going to play the 33-cent game in infinitesimally small time. That's what we will do. I hope not to lose anybody, but I will do exactly the same. I'll start again from here the week after. So if from what you get from here, say, wow, I was, floored, don't worry. Next week, I'll do it again. This is something that is worth doing twice. I don't mind repeating myself, okay? Okay, we take a 10-minute break and we come back at 1:25. The only thing I want to do in the half hour that remains is to show you how the 33-cent game can be played in infinitesimally small time increments, given what we have learned. Next week, I will try to give you some context around this. I will tell you how, in particular, the theory was discovered by Myron Scholes, and I'll make a reference to his Nobel laureate speech, which you can find on the website. But I just want to focus today on the game itself, on how what we've learned in stochastic calculus leads to a solution. It's just math that I'm going to do today. The finance aspect of that, as well as a review of what I'm doing now, is something that I will do next week. I want to make sure that all of this is understood. There are no doubts, but also I want to see the landscape that opens up once this theory is developed. Just the landscape. There are many things that can be done, but we're not going to do them. I will show that next week. So the way the 33-cent game is done in infinitesimal time frames is as follows. I'm going to assume that I have a derivative, a European option. Could be the same. If the stock, I cannot say goes up or down, I have to give you a strike price. I have a certain stock, certain price today, say $1 today. Instead of telling you whether it's going to go to $2.50, what I say is that it's going to evolve according to an Ito process, just like we did earlier. We know this is the extension of the 33-cent game. We know that. But now we use different language. I want to say drift mu, volatility sigma, as opposed to giving you just two values. This gives us infinitely many values, but we know these infinitely many values with what probabilities can be taken. We know that. It's an Ito process. That's what we've learned today. We have a new language to express future values of the stock. And there's a maturity time, just like in the case of the 33-cent game. It could be a day, it could be a year, it could be 10 years. There's a maturity time at which we see what the payoff is. The option gives you the right to buy the stock, not the obligation. That's one perspective. But from an arbitrage-free perspective, I prefer to talk about the payoff as if it's money that's given to you somehow. So I'm going to think of the payoff as a function, real valued function with a certain price, a certain dollar number attached to that. And it could be anything. It could be a call option. We've seen the payoff of a call option, which is S minus the strike price when it's positive and 0 when it's negative. But it doesn't matter. It's some function of S at maturity. So I denote it with F sub capital T of S. And the way we're going to play the game is I'm going to build the replicating portfolio directly for you. That is what changes. I will give you the replicating portfolio. It's going to be fairly simple to build because of all of the hindsight we have now, everything that we've learned. Still, the replicating portfolio will be not just the static portfolio. We've already seen that the portfolio changes over time. So it's going to be a strategy more than a portfolio. In other words, at every point in time, and as a function of every possible stock price, we will hold the number of stocks that we call A. Just like we did earlier, except that now A is a function of S and T. It's time dependent and price dependent. Note that this notation is consistent with our tree approach, how we did it when we had trees. And I'm also going to hold the number of bonds, meaning I may borrow money, I may lend money, so there's going to be a bond account. The bond account, bonds have deterministic values, so we know what they are. Stocks we don't, but bonds we do. Still, we will denote by B the number of bonds we will hold at every point in time as a function of the value of the stock at every point in time. So these are variables. Right? So these are random variables, which are a function of S and time. And now, what I'm going to do is I'm going to set up the replicating portfolio so that the price of the option as a function of S and T matches the value of the replicating portfolio. This is a desire I have. This is my objective. I'm not solving anything. I'm not telling you how A and B are calculated. I'm just telling you that's what I am aiming for. I'm aiming to have a function A and a function B, which I'm about to tell you what they are, that will have this characteristic. It matches the option price at all times, for all prices, and at maturity, it also equals the option price. That's the approach we're going to take. This is how we're going to play the 33-cent game in infinitesimal time. Okay? It's as if in the 33-cent game, I give you the replicating portfolio directly, which is what I did. I told you, if you give me the money, I buy this, and then. But now, because we're playing this at all times, at the same time, I'm not going to do this retroactively. I'm going to do this all at once. I'm not going to do backfill propagation, by the way. So to do that, I'm going to bring them a financial argument. And I want to tell you, the number of stocks I'm going to hold is equal, listen to this, to the partial derivative with respect to S of the function price at value S and at time t. Only mathematicians can do this. Only mathematicians can do this. I'm looking for the option price. I call it F. I don't know what it is. I don't know what F is, but I don't need to know what F is as long as I know, for example, that it's differentiable. Because if F exists, I can say the number of stocks will be this partial derivative. We don't know what it is either. Math allows us to do that. Some of you may be thinking, wait a minute, I need to know that F exists, that is unique, that it has derivatives. Yes, I know. I'm not doing that, as you can imagine. If F exists, I'm telling you, this is the number of stocks I'm going to hold. And you say, wow, Why? That's crazy. How do I know that? Well, I know that because not only because I know, you're about to find out. Okay, but let me give you these things one step at a time. And don't forget, this earned someone the Nobel Prize. Just like it earned Einstein the Nobel Prize. We're doing 2 Nobel Prizes in one day. That's pretty good. Okay? Pretty good. The first Nobel Prize with one picture, the second Nobel Prize in 2 pages. Not bad. Not bad. So with that, now I don't construct, I imagine a portfolio which is the option price minus this replicating portfolio that arises from the number of stocks I have at time t. And some bond units, which I don't know, and as you're about to find out, I don't need to know. That's the portfolio I have. What's the evolution of this portfolio? Well, it's here. That is a long equation. So no one, don't get alarmed. Don't get alarmed. Let's go step by step. Step by step. So this portfolio will evolve as follows. The evolution of this portfolio is the evolution of the option price. Fine, let me write it down. I don't know what it is, but I don't need to know, I just write it down. Then I have to apply the chain rule to A and B multiplied by the number of stocks that I have. And that corresponds to what you have here. This is the differentiation of the product. This is the differentiation of the product, okay? So in the differentiation of that product, I'm going to have this element here. This element here, by the way, no one has a question about this derivative, right? The derivative of A times S is S times derivative of A times derivative of S times A. And B times B, the derivative of that is derivative of B times B plus B times derivative of B. That's what I have. But I want to draw your attention to this term here. What this term here is, and again, I'm appealing to your intuition. Please use your intuition so I can do this in one page. Your intuition here should say that this is the number of stocks that I buy and sell times the cost of that, and the rebalancing of my loan times the value of my bond at that time. So this thing has to be equal to 0, because if every hedging activity we have done, when we rebalance the portfolio, we don't take in new money, we don't have profits, right? So this is what's called the self-financing condition. This is 0. We're going to buy as many, we're going to borrow as much money as we need to buy new stock. That's what this is saying. We've always done it. So we can impose that self-financing condition. I will borrow as much money as I need to buy new stock if I have to. And if I sell stock and I make money, I return the loan that I made earlier. That's what that means. This is a financial property. It's not mathematical, it's a financial property. Okay? So this term is 0, it disappears. Great, we got that. The next topic is DTF. What is that? Again, I don't know F, I don't know DTF, but I know Ito's lemma, and Ito's lemma will tell me that DTF is that. Okay? That's Ito's lemma. See that there? Harsh. Yes.
Quick question about when you took the derivative. Don't we need like the extra like drift term from the second order Taylor like expansion? Because right now it just looks like the terms are just like normal product rule.
You're looking at this?
Like the very first line, the very first line.
Oh, here?
Yeah, that line.
So what drift do you want here? Sorry, I didn't understand that.
No, like in like the last example with like the theory of like the Ito stuff that you developed, right?
Wait. No, I have not used Ito's lemma yet. That will be here. Of course,
Oh, okay.
this is coming. No, you're right. It's coming, but it happens in the second line. Okay?
Oh, okay.
Happens in the second line. Yes. You're right. But you know what? Maybe let me go a little bit more slowly. So that term is equal to 0. That's the self-financing condition. I already explained that. Okay? Now, this is Ito's lemma. I used Ito's lemma here, not earlier. Okay? I want to go step by step. I could do everything at the same time, but no, I did it after. You see, and that's where the term of Ito's lemma, the extra term, that's where it shows up. Everything else is as expected from traditional calculus, but this is extra. And dBT is that because bonds move with interest rates. They grow as interest rates. And for A, I'm plugging in its value, which is here. So that's why this is here. Okay? Okay? And now, this is the miracle. This is the miracle. As with the 33-cent game, we see that there's no uncertainty. In the 33-cent game, we show there was no uncertainty because no matter what happened to the stock, I always got 0. In this case, I see there is no uncertainty because that term and that term, they kill each other. They are the same. They are the same. And what I have left only has dt. There's no dw. dw is gone from that expression. You see, dw has disappeared. No dw. In the 33-cent game, I said I get 0 and I get 0. And here I don't get that. What I get is whatever this number is, there's no uncertainty in that number. That number is what it is, and whatever the stock does, we don't care. You see, it's the same as we did in the 33-cent game, except now this is what, variant number 8 or something? I don't know. See that? There's no DW. That means that no matter what the stock does, the answer is the same. So if the answer is the same, what is it? It has to be a bond. Only a bond gives you a value which is independent of the stock movement, right? That's the fundamental theorem of asset pricing. Absence of arbitrage. So this has to be a bond. This thing you're looking at is a bond. This portfolio, pi, is a bond. And because it's a bond, it moves like a bond. So this is number 0 by construction of A, and this portfolio is a bond. Therefore, if it's a bond, all of this that we have done, all of this expression is this. And remember, pi is here. So now what we have to do is this. That's what I'm going to do now. Okay? I'm going to substitute. I'm gonna use a different color. Here. Once I have that, I say this is equal to that. And that's an equation. That's an equation. You see that? Pi is here. Pi goes here. This and that is the same. Therefore, that equals that. That's the equation I have. After I plug in this for that. Okay, that's what I'm doing. I'm just plugging things. Everybody sees that? Do you have any questions? Do you want to see what the result is? That's what I have. That's the Black-Scholes equation, then becomes this. That's what happens when I replace the portfolio by its value. It's an equation. It's a differential equation. And we can rewrite it to resemble a diffusion equation, which may look more familiar to you as this. So the partial derivative with respect to time of the option price equals the interest rate times the option price minus interest rate times the derivative of the option price with respect to the stock price times the stock price minus 1/2 of the volatility of the stock squared times the stock price squared times the second derivative of the option price with respect to the stock, with the terminal condition that at expiration it has to be equal to the given payoff. I'm not telling you what the option price is, but I'm doing something which is just as good as that. I'm telling you the equation it must satisfy. The differential equation it must satisfy. And now you know, I mean, you've learned this in other courses, that instead of giving you a function, I give you a differential equation it's supposed to satisfy is just as good. You solve the differential equation, you have the function. That's all I want to do today. In the next slide, I solve it for you, but I don't want to do that. I want to end here. I want you to realize that we have joined two Nobel Prizes, Einstein and Merton and Scholes and Black. This thing we're doing here is the same thing we did with the Einstein theory. In financial terms, we didn't use temperature, we used money. We used arbitrage. Instead of saying that heat moves like that, I used absence of arbitrage. So I replaced physics with finance. And then I mimicked the argument that Einstein did in a financial context to get a similar equation, just like Einstein did. That's what we have gained today. Next week, I'll give you the full financial and economic consequences of this. I don't want to do that today. Okay? It was hard enough to climb the mountain of stochastic calculus. It was hard enough to do the math that allowed us to get here. But not only I did math, I did finance and I did physics. And I want everybody to realize that the physics and the finance are actually the same. Math is what makes them the same. This concept that diffusion processes express random walks. And differential equations is the solution to that. I have arrived where I wanted to be today. Are there any questions? We have a lot of time for questions. I understand this is not hard. Again, we've done the theory of two Nobel Prizes almost 100 years apart in one lecture. I understand that. Because of that, I will start from the Black-Scholes theory again next week, and then I'll tell you more, and we'll talk about the financial context, and we'll do very nice applications of all of this. Applications that will be very important when we do risk management, very important when we do credit trading. They're going to be with us forever, because this perspective will be very, very useful to understand what's to come later in this course. My objective today is that you have seen how stochastic calculus is built. We started with the example of a good student who made a mistake, a very interesting mistake. We saw how to fix the mistake and why from a very programmatic perspective of writing Python code. And from there, we say, well, if random walks behave like that, then let me do a baby theory of random walks, Ito processes, Ito's lemma. Once we became good at it, say, well, let me now bring finance, a financial argument into that, just like Einstein brought a physical argument into how temperature evolves, the same. Once I did that, I used an inside-out version of the 33-cent game to find a replicating portfolio implicitly, because I don't know the option price, I just know that it exists. But then we found it, and then the price of the option is expressed implicitly through the solution of this equation we have here. That's what we have gained today.